Alright, so at this point we will have done the experiment. And so I had kind of debated about whether or not I add this to the video, but I think I will, just because it's it's all nice to keep it in one spot. Alright, so Renin appears to have an optimal temperature of, that will be something you'll have to figure out. Alright, and the explanation, we're going to help walk you through this one, just so that you guys don't feel too under pressure with this one. So particles at lower temperature have a lower successful collision rate with enzymes. The more energy a particle has, the more it's going to bounce around, and the more it bounces around, the more chance it has of colliding with an enzyme. All right, so that's a pretty cool. Oh, sorry, that's a pretty cool concept to play with. All right, and something happens. We must have found something in our experiment that said that at high temperatures, mammalian enzymes are denatured. So this word denatured is going to crop up, and we kind of need to have a bit of discussion about it. It's a pretty important word. I wonder what you might think it means. Alright, so our discussion of the pH. Alright, Renin appears to have an optimal pH of... Dun, 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 you fill in the blank. Alright, so the explanation. Although Renin is a digestive enzyme and has an optimal pH of 2, commercial products. Rennet. We didn't use Renin, we used Rennet. Alright, and it's used for cheese. Alright, and this might have an optimal pH of around 5.5. And I reckon if you did that test on testing the pH of milk, you might find that those numbers are very close, because it is for cheese. Cheese is made from milk. Alright, so our results should have also shown that outside our optimal pH, enzyme activity was lower. I wonder if that did show in our results. Hopefully it did. That is a nice way of validating your results. We know that as pH, an enzyme, if it's in the gut, if that gut has a low pH, then higher pHs will denature the enzyme. All right, the last one. This is a interesting concept, and I think this is going to require a bit of discussion in class to kind of get our heads around. But what we get increased substrate concentration. It increases the activity of an enzyme to a point before activity plateaued. Now, plateaued is basically just kind of like leveling off. So, I'm not sure, did I? No, I didn't. At low concentrations, only some of the enzyme active sites are occupied. So this might mean that if you have I don't know, if I threw a ball to you, you could catch one ball, but if I could throw another ball to you, you could catch the second ball, and then your hands are full. If I keep throwing balls at you, you're not going to keep catching them. You're going to have to spend time and place those balls on the ground before you can catch another ball. This is what happens with an enzyme. The enzyme binds with a substrate, and then it has to spend time in order to produce a product. And so while it's bonded in that enzyme substrate complex, no other substrates can bond with it. So there is a bit of a time. Depending on the amount of enzyme you have, you are going to determine how much you can actually work with. So at some point, you get all enzymes are saturated, and then your activity is at a maximum. You're going to have to increase the amount of enzyme. Increasing the amount of substrate will only work to a point, and it's at that point where activity is at a maximum. And so on your graph, it should show that perhaps we get a maximum plateauing at some point. But I wonder if your graph doesn't show that. Why doesn't it? Anyway, that's our experiment. We'll be doing that in class, and hopefully you generate a few questions of your own, and we upskill you. You become better biologists, you become better students, and your critical thinking skills are improved.